There is not a single object in the observable universe that is perfectly still. Not one. Earth beneath your feet rotates at 1,600 kilometers per hour at the equator, fast enough that if friction suddenly vanished, you would be flung into space like a stone from a sling. The planet completes this rotation every 24 hours. One day, one spin. This has been happening for 4.5 billion years. Roughly 1.6 trillion rotations since Earth formed, and it will continue for billions more until the Sun dies and the planet becomes a frozen corpse orbiting a white dwarf remnant. But Earth's spin is just the beginning. The planet orbits the Sun at 107,000 kilometers per hour, 30 kilometers every second. The distance from New York to Boston crossed in 6 seconds. This orbital motion carries Earth through 940 million kilometers every year, a circle so vast that light takes 8 minutes to cross from Sun to Earth. Yet this enormous orbit is merely one component of a hierarchy of rotations, extending from microscopic scales to the entire observable universe. The Sun itself rotates. 25 days for one complete rotation at the equator, 35 days near the poles, because stars are not rigid bodies, but plasma that can rotate at different rates depending on latitude. This differential rotation creates the twisted magnetic fields that generate sunspots and solar flares and coronal mass ejections that sometimes strike Earth's magnetosphere, creating auroras visible from the poles. The Sun has completed roughly 180 million rotations since it formed 4.5 billion years ago. It will complete perhaps another 180 million before it exhausts its hydrogen fuel and begins the death process that transforms it into a red giant. The Sun does not sit motionless in space. It orbits the center of the Milky Way galaxy at 220 kilometers per second. The entire solar system tumbles through space following the Sun's gravitational lead. This galactic orbit takes 225 million years to complete. One cosmic year. Earth has completed roughly 20 galactic orbits since it formed. Dinosaurs lived and died during one partial orbit. Human civilization has existed for less than 1/10,000th of a galactic year. We are newcomers on a spinning world, orbiting a spinning star that itself orbits through a spinning galaxy. The Milky Way rotates. 600 million years for the galaxy to complete one full rotation. But this number is averaged. Stars near the galactic center orbit faster. Stars in the outer regions orbit slower. Except they do not orbit as slowly as they should. Orbital velocity should decrease with distance following Kepler's laws. But observations show that stars in the galactic outskirts move faster than their visible mass can explain. This is one of the primary pieces of evidence for dark matter, an invisible substance that provides the gravitational pull necessary to explain the galaxy's rotation curve. Dark matter does not emit light, does not interact electromagnetically, but it has mass, and that mass dominates the galaxy's gravitational field. Roughly 85% of the Milky Way's mass is dark matter. We see the stars and gas, but most of the mass, creating the gravitational well that organizes galactic rotation, remains invisible. Even galaxy clusters rotate. Though weakly, and over timescales of billions of years, the local group, containing the Milky Way and Andromeda and dozens of smaller galaxies, has some net angular momentum. The system as a whole tumbles slowly through space. Andromeda approaches at 110 kilometers per second. In 4 billion years, the two galaxies will collide. Their mutual gravitational interaction will scatter stars and heat gas, and eventually merge them into one larger elliptical galaxy. The collision will alter rotation patterns. Angular momentum will be redistributed. Some stars will be flung into intergalactic space. Others will settle into new orbits around the merged galactic center. But total angular momentum will be conserved. This is fundamental. This is law. Angular momentum conservation is one of the most fundamental principles in physics, right alongside energy conservation and momentum conservation. In any closed system, angular momentum cannot be created or destroyed. It can only be transferred between objects or converted between different forms. This conservation law emerges from rotational symmetry in physical laws. The fact that the laws of physics work the same regardless of orientation in space. Emmy Noether proved that every symmetry in nature corresponds to a conservation law. Translational symmetry gives momentum conservation. Time symmetry gives energy conservation. Rotational symmetry gives angular momentum conservation. This means the universe remembers every spin. Every rotation that has ever occurred since the Big Bang contributes to the total angular momentum budget. When a spinning object breaks apart, the fragments carry away angular momentum. When objects collide and merge, their angular momenta combine. But the total never changes. The universe at large has some fixed total angular momentum that was established at the moment of the Big Bang. Everything that spins draws from this primordial reserve. Every planet, every star, every galaxy, every black hole rotates because rotation existed from the beginning. But why did anything spin in the first place? Why did the Big Bang create angular momentum rather than a perfectly symmetric expansion where everything moved radially outward without rotation? The answer involves quantum fluctuations in the early universe. In the first fractions of a second after the Big Bang, quantum uncertainty created tiny variations in density and velocity. These variations were infinitesimal but real, random quantum jitters in spacetime itself. As the universe expanded and cooled, these quantum fluctuations were stretched to cosmic scales. Regions with slightly higher density attracted more matter. Regions with slight velocity differences developed rotational motion. Imagine a vast cloud of gas expanding after the Big Bang. The cloud is not perfectly uniform. Quantum fluctuations have created slight density variations. One region is marginally denser than average. Gravity begins pulling surrounding material toward this dense region, but the material does not fall straight in. Small random velocities cause it to miss the center. Instead of collapsing radially, the material begins orbiting. As more material accumulates, conservation of angular momentum causes the rotation to accelerate. The cloud flattens into a disk. Material in the disk continues spiraling inward while rotating faster and faster. Eventually, the center becomes dense enough and hot enough to ignite nuclear fusion. A star is born, and it is spinning because the cloud from which it formed was spinning. And the cloud was spinning because quantum fluctuations in the early universe gave it infinitesimal angular momentum that amplified over billions of years through gravitational collapse. This is how the Sun formed. 4.5 billion years ago, a giant molecular cloud spanning several light years began collapsing, perhaps triggered by a nearby supernova shockwave, perhaps simply through gravitational instability when the cloud exceeded its Jeans mass, the critical threshold where self-gravity overcomes thermal pressure. As the cloud collapsed, rotation increased. Not uniformly, the cloud fragmented into smaller collapsing regions. Each fragment began forming its own star or planetary system. The fragment that became our solar system was already rotating when it started collapsing. Conservation of angular momentum dictates that as the cloud shrank, it had to spin faster, like an ice skater pulling in their arms during a spin. The rotation rate increases to conserve angular momentum as the moment of inertia decreases. The collapsing solar nebula spun faster and faster. Centrifugal effects prevented collapse in directions perpendicular to the rotation axis. Material could fall inward along the poles, but not along the equator. The cloud flattened into a disk, a protoplanetary disk. The Sun formed at the center, where most of the mass accumulated. The planets formed from the remaining disk material through accretion. This explains why all planets orbit the Sun in the same direction and roughly the same plane. They inherited the angular momentum of the original rotating cloud. The solar system's orbital geometry preserves the rotation axis of the cloud that collapsed 4.5 billion years ago. Every planet moving counterclockwise when viewed from above Earth's North Pole. Mercury at 47 kilometers per second, Venus at 35, Earth at 30, Mars at 24. The orbital velocities decrease with distance, following Kepler's laws, but all orbit the same direction, because all formed from the same rotating disk. But the planets do not just orbit, they also rotate on their own axes. Earth spins once every 24 hours. Mars spins every 24.6 hours. Jupiter completes a rotation in just 10 hours, despite being 11 times Earth's diameter. Saturn takes 10.5 hours. These rotations also derive from the protoplanetary disk. As planetesimals collided and merged during planet formation, they brought their own angular momenta. Random impacts from all directions could in principle cancel out, producing a non-rotating planet. But perfect cancellation is statistically unlikely. Some net rotation almost always remains. The direction and rate depend on the specific history of impacts during accretion. Jupiter rotates fastest because it formed earliest and accreted most material. As gas from the protoplanetary disk fell onto the proto-Jupiter, it brought angular momentum. The gas did not fall straight in, but spiraled around the growing planet. This spiral motion added angular momentum, causing the planet to spin. The more mass Jupiter accumulated, the more angular momentum it acquired. By the time Jupiter reached its current mass, roughly 318 Earth masses, it had accumulated enormous angular momentum. This angular momentum cannot be lost easily. Jupiter will continue spinning at roughly its current rate for billions of years. Tidal interactions with its moons slowly transfer angular momentum, causing gradual spin down. But the timescale is so long that Jupiter's rotation rate has changed negligibly since formation. Earth's rotation is more complex. The planet likely formed spinning much faster, perhaps completing a rotation every 6 hours. But a collision early in Earth's history dramatically altered its rotation. Roughly 4.5 billion years ago, a Mars-sized protoplanet designated Theia struck Earth in a glancing impact. The collision was catastrophic. The impact vaporized Theia and much of Earth's mantle. Debris was flung into orbit, where it coalesced into the Moon. The giant impact changed Earth's rotation rate and possibly its axial tilt. The current 24-hour day and 23-degree axial tilt might be direct consequences of this ancient collision. The Moon itself does not appear to rotate when viewed from Earth. The same face always points toward us, the near side, with its dark maria and bright highlands. The far side remained hidden until spacecraft photographed it in 1959. But the Moon does rotate, one rotation every 27.3 days, exactly the same period as its orbit around Earth. This is called tidal locking, a synchronous rotation where orbital period equals rotational period. Tidal locking is not coincidence. It results from tidal forces between Earth and Moon. Here is how tidal locking works. The Moon raises tides on Earth. Ocean water on the side facing the Moon is pulled toward it, creating a tidal bulge. Water on the opposite side is pulled less, creating another bulge. Earth rotates faster than the Moon orbits. The tidal bulges try to rotate with Earth, but the Moon's gravity pulls them back. This creates friction. The friction dissipates rotational energy as heat. Earth's rotation gradually slows. Currently, the day lengthens by about 1.7 milliseconds per century. This seems negligible, but over billions of years it adds up. Hundreds of millions of years ago, days were significantly shorter. Coral growth rings and sedimentary layers preserve evidence that 620 million years ago, a day was only 21.9 hours. Earth has been spinning down throughout its history. but angular momentum is conserved. Earth's rotational angular momentum cannot simply disappear. It is transferred to the Moon's orbital angular momentum. As Earth's rotation slows, the Moon recedes. Currently, the Moon moves away from Earth at 3.8 centimeters per year. Over geological time, this adds up to significant distance changes. When the Moon formed, it was perhaps 15,000 kilometers from Earth. Today, it is 384,000 kilometers distant. It will continue receding until Earth becomes tidally locked to the Moon. At that point, Earth will rotate once per lunar orbit. One face of Earth will always point toward the Moon. Days and months will be equal in length, roughly 50 current days. But this equilibrium lies billions of years in the future and will likely never occur because the Sun will become a red giant first. The Moon experienced its own tidal locking much faster because Earth's tidal forces on the Moon are stronger than the Moon's forces on Earth. Earth has 80 times more mass. The tidal bulges Earth raises on the Moon are correspondingly larger. These bulges created friction in the Moon's interior when it still had a molten core. The friction dissipated the Moon's rotational energy. Within perhaps 100 million years after formation, the Moon became tidally locked. Its rotation slowed until rotational period matched orbital period. Now the Moon keeps the same face toward Earth permanently. The far side experiences the same day-night cycle, but never sees Earth in its sky. Most moons in the solar system are tidally locked to their planets. Jupiter's 4 large Galilean moons all show one face to Jupiter. Saturn's largest moons are similarly locked. Pluto and its large moon Charon are mutually tidally locked. Each keeps the same face toward the other. Charon only ever sees one hemisphere of Pluto and vice versa. This represents the end point of tidal evolution. Both bodies are locked. Neither can exchange angular momentum with the other. The system has reached equilibrium. But not all rotations in the solar system follow the standard pattern. Venus rotates backward, retrograde rotation. All other planets rotate in the same direction they orbit. Venus rotates in the opposite direction. One Venusian day takes 243 Earth days, longer than Venus's year, which is 225 Earth days. This means the Sun rises in the west and sets in the east on Venus, but so slowly that a Venusian day exceeds a Venusian year. You could walk fast enough on Venus to keep the Sun stationary in the sky. Simply walk westward at the appropriate speed, and the Sun never moves relative to you. You experience eternal sunset or sunrise, depending on your chosen position. Why does Venus rotate backward? The answer is uncertain, but likely involves ancient impacts. Early in solar system history, when planetary formation was violent, Venus was probably struck by multiple large planetesimals. These impacts could have altered its rotation. A sufficiently massive impact from the right direction could reverse rotation entirely. Or perhaps Venus originally rotated forward, but tidal interactions with the Sun reversed it. Venus has no large moon like Earth's to stabilize its rotation. The Sun's tidal forces, acting on Venus's thick atmosphere, might have gradually reversed the planet's spin over billions of years. Or perhaps chaotic interactions with other planets during the solar system's early dynamic phase caused the reversal. We cannot know with certainty. The evidence has been erased by 4 billion years of subsequent evolution. Uranus has an even stranger rotation. Its axis is tilted 98 degrees, almost lying on its side. The planet rotates perpendicular to its orbital plane. During part of Uranus's 84-year orbit, one pole points nearly at the Sun. That pole experiences 42 years of continuous daylight, while the other hemisphere remains in darkness. Then, as Uranus continues in its orbit, the poles reverse roles. The previously dark pole enters decades of sunlight, while the previously lit pole enters decades of darkness. The equatorial regions experience more typical day-night cycles, but the Sun travels almost vertical paths across the sky, rather than rising in the east and setting in the west. This extreme axial tilt almost certainly results from one or more giant impacts early in Uranus's history. A collision with an Earth-sized protoplanet could knock Uranus onto its side. The impact would have been devastating. The planet's interior would have been heated, material would have been vaporized and ejected. But Uranus survived. Its odd rotation is a permanent reminder of ancient violence during the solar system's formation era. These examples demonstrate that while rotation is universal, the specific properties of rotation depend on formation history and subsequent evolution. Every spinning object tells a story. Earth's 24-hour day and its moon reflect the giant impact 4.5 billion years ago. Venus's retrograde rotation hints at chaotic early collisions. Uranus lying on its side preserves evidence of catastrophic impact. Jupiter's rapid 10-hour rotation records the enormous angular momentum it acquired while forming. Each rotation rate, each axial tilt, each orbital configuration, all are fossils, preserving information about processes that occurred billions of years ago. Even small objects rotate. Asteroids tumble through space with rotation periods ranging from hours to days. Some asteroids are contact binaries, two objects touching or nearly touching that orbit their mutual center of mass while also rotating individually. The asteroid Bennu, visited by the OSIRIS-REx mission, rotates every 4.3 hours, fast enough that loose material on the surface experiences significant centrifugal effects. The asteroid's shape bulges at the equator, creating a spinning top appearance. If Bennu rotated much faster, it would fly apart. The gravitational force holding it together is weak. Centrifugal effects nearly overcome gravity already. Bennu sits close to the spin limit for a rubble pile asteroid. Some asteroids rotate much faster. Small asteroids only a few meters across can complete rotations in minutes. The asteroid 2008 HJ has a rotation period of just 42.7 seconds. It spins so fast that surface gravity is overwhelmed by centrifugal force. Only internal cohesion keeps it intact. If 2008 HJ were a rubble pile held together only by gravity, it would disintegrate immediately. The fact that it survives proves the asteroid must be a single solid rock, or at least have significant internal strength. Comets also rotate as they hurtle through the solar system on their elongated orbits. Comet 67P, Churyumov-Gerasimenko, visited by the Rosetta spacecraft, rotates every 12.4 hours. As the comet approaches the Sun and begins outgassing, jets of water vapor and dust erupt from the surface. These jets are not uniformly distributed. They tend to emerge from the sunlit side, where frozen volatiles sublimate. The jets create thrust, like rocket engines firing. This thrust can alter the comet's rotation. Observations show that 67P's rotation period changed slightly during its 2015 perihelion passage. The jets acting for weeks as the comet rounded the Sun imparted enough angular momentum to measurably affect the rotation rate. This demonstrates another fundamental principle. Rotation can be changed by external torques. Angular momentum is conserved, but it can be transferred. When comet jets fire, they push against the comet, creating torque. The comet's rotation changes in response. When tidal forces act on planets and moons, angular momentum is exchanged between rotation and orbital motion. When stellar winds blow away material from rotating stars, they carry angular momentum. The star's rotation slows as a result. All these processes conserve total angular momentum while redistributing it between different objects and different forms. The Sun itself has lost most of its original angular momentum. Based on the solar system's total angular momentum, and assuming it all began in a rotating cloud, the Sun should be spinning much faster than observed. Most of the angular momentum ended up in planetary orbits rather than solar rotation. This transfer occurred during formation. As the protoplanetary disk evolved, Magnetic fields coupled the disk to the young sun. The fields transferred angular momentum outward from the sun to the disk. This magnetic braking slowed the sun's rotation while accelerating disk material. By the time planet formation completed, the sun rotated slowly while planets orbited rapidly. The sun contains 99.86% of the solar system's mass, but only about 2% of its angular momentum. The planets, especially Jupiter, carry most angular momentum in their orbital motion. This pattern repeats throughout the universe. Wherever rotating systems form through gravitational collapse, angular momentum is redistributed. Star formation always involves magnetic braking that transfers angular momentum from the central star to surrounding material. Planet formation involves collisions and tidal interactions that distribute angular momentum among planets and satellites. Galaxy formation involves mergers and interactions that convert orbital angular momentum into internal velocity dispersion. The specific mechanisms differ, but the underlying principle remains. Angular momentum is conserved. It cannot be created or destroyed, only moved around. Here is what makes rotation truly fundamental. Angular momentum is a vector. It has magnitude and direction. The magnitude represents how fast something spins. The direction represents the spin axis. In three-dimensional space, the direction is specified by a vector pointing along the rotation axis. By convention, the direction is determined by the right-hand rule. If you curl your right hand's fingers in the direction of rotation, your thumb points along the angular momentum vector. Earth's angular momentum vector points through the North Pole. Jupiter's points through its North Pole. The Sun's points through its North Pole, though tilted 7 degrees relative to the ecliptic plane. When two rotating objects interact, their angular momentum vectors add like ordinary vectors. If two objects rotate in the same direction and merge, their angular momenta add. The combined object rotates faster. If two objects rotate in opposite directions and merge, their angular momenta partially cancel. The combined object might rotate slowly, or not at all, depending on the magnitudes. This vector addition is how angular momentum is conserved during collisions and mergers. The total angular momentum vector before collision equals the total after collision. Magnitude and direction are both conserved. This becomes important in astrophysical contexts. When galaxies collide, they bring enormous angular momenta with different directions. The merger produces a remnant with net angular momentum that is the vector sum of the original angular momenta. This determines whether the remnant becomes a rotating disk galaxy or a non-rotating elliptical galaxy. If the colliding galaxies had similar angular momenta in the same direction, the remnant preserves rotation and becomes a disk. If the angular momenta were in opposite directions or at large angles, they partially cancel, and the remnant becomes an elliptical with little net rotation. When stars form in binary or multiple systems, angular momentum is distributed between orbital motion and stellar rotation. Closed binary stars transfer angular momentum through tidal interactions. The stars slow their rotation, while the orbit tightens or expands, depending on whether rotation is faster or slower than orbital motion. Some binary systems reach equilibrium, where both stars are tidally locked, showing the same face to each other, like Pluto and Charon. Others continue evolving. White dwarf binaries slowly spiral together as gravitational waves carry away angular momentum. The orbit shrinks. The orbital period decreases. Eventually, the stars merge. The collision creates a single, more massive object whose properties depend on the vector sum of the original angular momenta. Angular momentum even affects the ultimate fate of matter. When massive stars collapse into neutron stars or black holes, angular momentum is conserved. A slowly rotating star might produce a slowly rotating neutron star. A rapidly rotating star produces a rapidly rotating neutron star or black hole. The rotation rate affects what happens next. Rapidly rotating neutron stars become pulsars. Beams of radiation emerge from magnetic poles. As the star rotates, these beams sweep across space like lighthouse beams. If Earth happens to lie in the beam path, we detect regular pulses of radio waves or X-rays. Some pulsars rotate hundreds of times per second. These millisecond pulsars are the fastest rotating objects known. They achieve such extreme rotation through accretion. Matter falling onto the neutron star from a companion star carries angular momentum. The neutron star spins up. Over millions of years, accretion can accelerate a neutron star from slow rotation to hundreds of rotations per second. Black holes also rotate. General relativity allows rotating black hole solutions called Kerr black holes. A Kerr black hole has angular momentum. The space-time around it is dragged by the rotation. This frame dragging effect becomes extreme near the event horizon. Close enough to the black hole, space-time itself rotates. Nothing can remain stationary. Everything is forced to orbit in the same direction as the black hole's rotation. This region is called the ergosphere. It lies outside the event horizon. Material in the ergosphere can still escape, but it must orbit the black hole. It cannot hover stationary, and it cannot orbit in the opposite direction. The rotation of space-time prevents this absolutely. Here is what should disturb you about rotation. It is ubiquitous, unavoidable, fundamental. Nothing in the universe is exempt. From quantum mechanical spin of fundamental particles to rotation of galaxy superclusters, from electrons orbiting nuclei to stars orbiting galactic centers, everything spins, everything orbits. Angular momentum permeates reality at every scale, and it can never be destroyed. The rotation that began with quantum fluctuations in the early universe persists today, 13.8 billion years later. Every spin you observe, whether a figure skater or a planet or a galaxy, contains angular momentum that has existed since the Big Bang. The universe is made of matter and energy and space and time, but it is also made of rotation. Angular momentum is as fundamental as mass or electric charge. It cannot be switched off or eliminated, only transformed, only transferred between objects, but always conserved, always present. This is what we discover when we look carefully at the universe. Everything moves, everything spins, nothing is truly at rest. Even objects that appear stationary are hurtling through space at hundreds or thousands of kilometers per second, participating in multiple nested rotations. You sitting reading this are rotating with Earth at 1,600 kilometers per hour and orbiting the Sun at 107,000 kilometers per hour and orbiting the galactic center at 792,000 kilometers per hour and falling toward the Andromeda galaxy at 110 kilometers per second. Your velocity relative to the cosmic microwave background rest frame is roughly 630 kilometers per second. You are moving, always spinning through space, and you have no choice because angular momentum was built into the universe from the beginning. This is just the first part of the story. We have explored why planets and moons and asteroids and comets rotate, how angular momentum conservation governs solar system dynamics, how tidal forces exchange angular momentum between rotation and orbital motion. But the universe contains objects far stranger than planets. Objects that rotate so fast, they challenge our understanding of what matter can endure. Objects whose rotation warps space-time itself. Objects spinning hundreds of times per second, thousands of times per second, approaching the maximum rate Einstein's equations allow. This is where we turn next, to the fastest rotations in the universe, to pulsars and black holes and the extreme physics of rotation pushed to its absolute limits. There is an object in the universe that completes 700 rotations every single second. not 700 rotations per hour, not per minute, per second. 700 full spins in the time it takes you to say the word second. This object is not small. It is not a particle or a molecule or even a dust grain. It is a neutron star, a stellar corpse containing more mass than the Sun, compressed into a sphere 20 kilometers across. And it is rotating so fast that its equator moves at roughly 20% the speed of light. Material on the surface experiences centrifugal acceleration millions of times stronger than Earth's gravity. The star is barely held together by its own gravity, rotates slightly faster, and it would tear itself apart. Fling pieces into space at relativistic velocities. This is PSRJ 1748-2446 AD, the fastest rotating neutron star ever discovered, the fastest rotating macroscopic object in the known universe. And understanding why it spins so fast requires understanding the most extreme rotations in nature. Begin with ordinary stars. The Sun rotates once every 25 days at the equator. This is slow, leisurely by stellar standards, but the Sun is a middle-aged star. It has been spinning down throughout its lifetime. When the Sun formed 4.5 billion years ago, it probably rotated much faster, perhaps once every few days. Young stars rotate rapidly because they form from collapsing rotating clouds. As the cloud contracts, rotation accelerates through angular momentum conservation. The proto-sun spun quickly, but stellar rotation does not remain constant. It decreases over time through a process called magnetic braking. Here is how magnetic braking works. The Sun has a magnetic field generated by convection currents in its interior. This field extends far beyond the visible surface into the solar wind. The charged particles in the solar wind follow magnetic field lines. As the Sun rotates, it tries to drag the magnetic field and the attached solar wind with it. But the solar wind extends far into space, millions of kilometers. The moment of inertia is enormous. The Sun cannot easily rotate this extended structure. Instead, the field lines twist. They become wound up by the rotation. This creates tension. The twisted fields exert torque on the Sun, slowing its rotation. Angular momentum is transferred from the Sun to the solar wind. The wind carries the angular momentum away into space. The Sun spins down. This process has been operating for billions of years. The Sun's rotation has decreased from perhaps one rotation every few days to one rotation every 25 days. This is a factor of 5 to 10 slowdown. Over the next 5 billion years, the Sun will continue slowing. By the time it becomes a red giant, it might rotate once every 50 or 100 days. When it finally sheds its outer layers and becomes a white dwarf, the remnant core will rotate much faster. Not because angular momentum increased, but because the moment of inertia decreased dramatically. A white dwarf is roughly Earth-sized, the Sun's core compressed to a fraction of its current radius. Conservation of angular momentum dictates that rotation rate must increase as radius decreases. A slowly rotating Sun with a 50-day period would become a white dwarf rotating every few hours. The same total angular momentum concentrated in a much smaller object. Some stars rotate much faster than the Sun. Young massive stars can complete rotations in hours. The star Beta Pictoris rotates every 16 hours despite being 1.8 times more massive than the Sun. The star Altair rotates in just 8.9 hours. It is so flattened by centrifugal effects that the equatorial diameter exceeds the polar diameter by roughly 20%. The star is visibly oblate, not a sphere but an ellipsoid. This is what happens when rotation becomes significant compared to gravity. The star bulges at the equator. Material experiences less net gravity there because centrifugal effects partially cancel gravitational pull. The star assumes a flattened shape where gravitational and centrifugal forces balance. The fastest rotating normal star ever discovered is VFTS 102 inches, the Large Magellanic Cloud. It rotates with an equatorial velocity of roughly 600 kilometers per second. The star completes one rotation in less than a day, despite being much larger than the Sun. This is approaching the breakup velocity. Rotate much faster, and the star cannot hold itself together. Material at the equator would be flung into space. VFTS 102 probably formed through binary interaction. Perhaps it was once in a close binary system. The companion star transferred mass and angular momentum. VFTS 102 spun up until it reached near breakup velocity. Then the binary evolved further. Perhaps the companion exploded as a supernova. VFTS 102 was left as a rapidly rotating single star, barely holding together against centrifugal forces. But even VFTS 102 cannot approach the rotation rates achieved by stellar remnants. When massive stars die, they leave behind neutron stars. These objects form during supernova explosions. The stellar core implodes. Protons and electrons are forced together, creating neutrons. The core becomes neutron matter. Material at nuclear density, 10 to the 14 grams per cubic centimeter. A teaspoon of neutron star material would weigh 1 billion tons on Earth. This density exceeds atomic nuclei. Neutrons are packed as tightly as neutrons in atomic nuclei, but now extended across a stellar mass object 20 kilometers in diameter. Neutron stars inherit the angular momentum of the collapsing core. The core before collapse might be the size of Earth. It rotates perhaps once per hour, not particularly fast. But as it collapses to 20 kilometers radius, rotation accelerates dramatically. Conservation of angular momentum requires that rotation rate increase as the moment of inertia decreases. The moment of inertia scales as mass times radius squared. The mass stays roughly constant during collapse, but the radius decreases by a factor of thousands. The moment of inertia decreases by a factor of millions. To conserve angular momentum, rotation rate must increase by a factor of millions. A core rotating once per hour becomes a neutron star rotating hundreds of times per second. This is why newly formed neutron stars are born rotating rapidly. They cannot avoid it. Angular momentum conservation guarantees it. The fastest rotating neutron stars complete hundreds of rotations per second. These are called millisecond pulsars because their rotation periods are measured in milliseconds. PSR J1000 748 2446 AD rotates 716 times per second, one rotation every 1.4 milliseconds. This seems impossible. How can an object 20 kilometers across containing more mass than the Sun rotate this fast? The equatorial velocity is roughly 70,000 kilometers per second, 23% the speed of light. Material on the surface experiences extreme conditions. Gravitational acceleration is 200 billion times Earth's surface gravity. Centrifugal acceleration partially offsets this, but the net gravity is still enormous. Neutron star material can withstand these stresses because neutrons are held together by the strong nuclear force, the same force that binds atomic nuclei. Neutron star matter is essentially one giant nucleus 20 kilometers across. But there are limits. Rotate too fast, and even neutron star material cannot hold together. The maximum rotation rate depends on the neutron star's mass and radius, both of which depend on the equation of state for ultra-dense matter. We do not know this equation of state precisely. Nuclear physics at these densities is uncertain. Laboratory experiments cannot recreate neutron star interior conditions. Theoretical calculations make predictions, but they diverge. Different models predict different maximum rotation rates. Most estimates suggest neutron stars cannot exceed roughly 1,000 rotations per second. Above this rate, the centrifugal force overwhelms gravity, even for neutron matter. The star would break apart. PSR J 1000 748 2446 AD rotating at 716 times per second, is approaching this theoretical limit. It cannot spin much faster without self-destructing. How did PSRJ 1748-2446 AD achieve such extreme rotation? It was not born this fast. Newly formed neutron stars rarely exceed 100 rotations per second. PSRJ 1748-446 AD was spun up over millions of years through accretion. The neutron star is in a binary system. It has a companion star. Material from the companion falls onto the neutron star. As the material spirals inward, it forms an accretion disk. The disk rotates around the neutron star. When material from the disk finally impacts the neutron star surface, it transfers angular momentum. The neutron star spins up. Over millions of years, continuous accretion can accelerate a slowly rotating neutron star to millisecond periods. This recycling process creates millisecond pulsars, old neutron stars rejuvenated by accretion-driven spin-up. Neutron stars emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space. If Earth lies in the beam path, we detect pulses of radio waves or X-rays. 1 pulse per rotation. These are pulsars. The name comes from pulsating radio source. Early astronomers thought they had detected signals from extraterrestrial civilizations. The pulses were so regular, so precise. But they came from all directions in the sky. Too many sources to be artificial. Eventually, the pulsar model was confirmed, rotating neutron stars with lighthouse beams of radiation. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell. She detected radio pulses with a period of 1.337 seconds, regular as clockwork. This was CP 1919. The Cambridge pulsar at coordinates corresponding to 19 hours 19 minutes right ascension. Subsequent observations found dozens more pulsars, all with periods between milliseconds and seconds, all astonishingly regular, the most stable clocks in nature. Some pulsars keep better time than atomic clocks over short timescales. The rotation is so regular because neutron stars have enormous moments of inertia. Once spinning, they do not slow down quickly. Millisecond pulsars are especially stable because they rotate so fast. Their angular momentum is enormous. They will continue rotating at nearly constant rates for billions of years. But pulsars do slow down, gradually, imperceptibly, but measurably, over years or decades of observation. The slowdown occurs because the rotating magnetic field creates electromagnetic radiation. This radiation carries energy and angular momentum away from the pulsar. The pulsar spins down. Young pulsars with strong magnetic fields slow down quickly. The Crab pulsar rotates 30 times per second. It slows down by roughly 1 rotation every 2,500 years. This seems slow, but it is detectable. The Crab pulsar is only 1,000 years old. It formed in the supernova of 1054 AD, observed by Chinese and Arabic astronomers. Despite its youth, it has already slowed measurably since formation. Millisecond pulsars slow down much more slowly. Their magnetic fields are weaker. They lose angular momentum more gradually. PSR J 1748-2446 AD will take billions of years to slow significantly. Some pulsars exhibit glitches, sudden increases in rotation rate. These occur when the neutron star's crust fractures. Imagine the star as a rigid crust surrounding a superfluid interior. The crust is crystalline, a lattice of neutrons and protons and electrons locked in place. As the pulsar slows down, the crust deforms. The centrifugal force decreases, but the crust maintains its oblate shape temporarily. Stress builds up. Eventually the crust fractures, a starquake. the crust suddenly adjusts to a less oblate configuration. The moment of inertia decreases slightly. To conserve angular momentum, rotation rate increases. The pulsar spins up suddenly, a glitch. These glitches are rare. They occur perhaps once per decade for a typical pulsar. But when they happen, they provide information about the neutron star's interior structure. The glitch magnitude and subsequent relaxation time reveal properties of the superfluid interior and crustal rigidity. Now consider galaxies. The Milky Way rotates. Our solar system orbits the galactic center at 220 kilometers per second. This orbital velocity is determined by the mass enclosed within our orbit. Using Kepler's laws, we can calculate that there are roughly 100 billion solar masses inside the Sun's orbit. This includes stars and gas and dust and dark matter, mostly dark matter. Dark matter comprises roughly 85% of the galaxy's mass. We cannot see it directly, but we detect it through its gravitational effects on visible matter. The galaxy's rotation curve reveals dark matter's presence. Measure the orbital velocities of stars and gas at different distances from the galactic center. Plot velocity versus distance. Classical physics predicts velocity should decrease with distance, following Kepler's laws, like planets in the solar system. Mercury orbits faster than Earth, which orbits faster than Jupiter, but galactic rotation curves are flat. Stars in the galaxy's outskirts orbit at roughly the same velocity as stars closer to the center. This violates Keplerian expectations. The only explanation is additional unseen mass, providing extra gravitational pull, dark matter, a halo of invisible material surrounding and permeating the galaxy, creating a gravitational potential that maintains high orbital velocities even at large distances. The Milky Way is not alone in this. All spiral galaxies show flat rotation curves. All require dark matter to explain their rotation. Andromeda rotates. M31, the nearest large galaxy to the Milky Way. It is also a spiral, also surrounded by a dark matter halo, also rotating with a flat velocity curve that defies classical expectations. In 4 billion years, Andromeda will collide with the Milky Way. The two galaxies will pass through each other. Stars rarely collide because interstellar distances are vast, but gravitational interactions will scatter stars. Heat gas trigger bursts of star formation. The galaxies will merge. Their dark matter halos will combine. The rotation will be disrupted temporarily, but angular momentum will be conserved. The merged galaxy will eventually settle into a new configuration, probably an elliptical galaxy, a spheroidal distribution of stars with little net rotation. Most of the original angular momentum converted into random stellar motions rather than organized rotation. Some galaxies rotate faster than others. Spiral galaxies with prominent disks rotate rapidly. Elliptical galaxies with little disk structure rotate slowly, or not at all. The difference reflects formation history. Spirals formed from rotating gas clouds that settled into disks. The rotation was preserved as stars formed within the disk. Ellipticals formed from mergers of galaxies with different rotation axes. The angular momenta partially cancelled during mergers. The remnants have little net rotation, but individual stars within ellipticals move rapidly. The velocity dispersion is high. Stars orbit in all directions. The total kinetic energy might equal or exceed that of a rotating spiral, but the motion is random rather than organized. This is what happens when rotation is disrupted by chaotic mergers. Now consider black holes. General relativity predicts that black holes can rotate. In fact, most black holes probably do rotate because they form from rotating objects. When massive stars collapse, they create rotating black holes. When gas accretes onto black holes, it transfers angular momentum. The black hole spins up. Unlike neutron stars, black holes have no maximum rotation rate imposed by material strength. but they do have a theoretical maximum imposed by general relativity. This is the extremal Kerr limit, the maximum angular momentum a black hole can possess given its mass. The limit is expressed as a dimensionless spin parameter, A equals jc divided by gm squared, where j is angular momentum, m is mass, g is gravitational constant, and c is speed of light. For non-rotating Schwarzschild black holes, A equals 0. For maximally rotating extremal Kerr black holes, A equals 1. Real black holes probably have spin parameters between 0 and 1, but many might approach A equals 1. Theory suggests that accretion naturally spins black holes up toward the extremal limit. As matter falls in, it transfers angular momentum. The black hole approaches A equals 1 asymptotically, but never quite reaches it. A rotating black hole has several distinctive features. First, it has two event horizons, an outer horizon and an inner horizon. The inner horizon lies within the outer and marks a boundary inside which the geometry becomes even stranger. But nothing can escape from beyond the outer horizon regardless. Second, the rotating black hole is surrounded by the ergosphere, a region outside the event horizon where spacetime is dragged around by the black hole's rotation. Inside the ergosphere, nothing can remain stationary. Everything must orbit in the same direction as the black hole rotates. This frame dragging effect becomes stronger, closer to the event horizon. The ergosphere has a bizarre property. It is theoretically possible to extract energy from a rotating black hole using the Penrose process. Send a particle into the ergosphere, have it split into two particles. Arrange the split so one particle falls into the black hole with negative energy relative to infinity, while the other escapes with more energy than the original particle. This does not violate conservation laws because the black hole loses mass and angular momentum. The escaping particle carries away more energy than the original particle brought in. The difference comes from the black hole's rotational energy. The black hole spins down slightly. This process could theoretically power advanced civilizations if they could build structures around rotating black holes. In practice, the Penrose process is probably not the main way rotating black holes lose energy. Magnetic fields threading through the ergosphere provide another mechanism, the Blandford-Znarek process. A rotating black hole surrounded by a magnetized accretion disk can generate powerful jets. The rotating black hole drags magnetic field lines. This creates electric currents and electromagnetic fields that accelerate particles to relativistic speeds. The particles are funneled into jets perpendicular to the accretion disk. These jets can extend for thousands or millions of light years. They carry away enormous energy and angular momentum extracted from the black hole's rotation. Some jets move at 99.9% light speed. They punch through intergalactic space, creating radio lobes visible across the universe. Sagittarius A star is the supermassive black hole at the Milky Way's center. It contains 4 million solar masses. Recent observations suggest it rotates rapidly, possibly near the extremal limit. Its spin parameter might be 0.9 or higher. This rapid rotation comes from billions of years of accretion. Gas and stars falling into the black hole brought angular momentum. The black hole spun up. Currently, Sagittarius A star is quiescent. It accretes very little material. The luminosity is tiny, but magnetic field measurements indicate rapid rotation. The field structure around the black hole shows twisting consistent with strong frame dragging. This suggests a spin near the maximum allowed by general relativity. When black holes merge, their angular momenta combine. LIGO has detected dozens of black hole mergers through gravitational waves. When two black holes spiral together and collide, they create a single, more massive black hole. The remnant's angular momentum equals the vector sum of the original angular momenta plus the orbital angular momentum at merger. For non-spinning black holes merging from a circular orbit, roughly 3% of the total mass is radiated away as gravitational waves. The energy carried by gravitational waves comes from orbital energy. The merger converts orbital kinetic energy into gravitational radiation. The final black hole rotates because it inherited orbital angular momentum from the pre-merger binary. Typical spins of merger remnants are moderate, spin parameters around 0.7, not extremal but significant. What happens when two maximally rotating black holes with aligned spins merge? Do they create a faster rotating black hole? No, they cannot exceed the extremal limit. Instead, some angular momentum must be carried away by gravitational waves. The merger produces a black hole near the extremal limit, but not beyond. General relativity forbids a greater than 1. This is the cosmic censorship conjecture. No naked singularities. Every singularity must be hidden behind an event horizon. And a greater than 1 black hole would be a naked singularity. The ring singularity inside a Kerr black hole would be visible from outside. This is believed impossible, though never rigorously proven. Nature apparently forbids exceeding the rotation limit. Black holes can approach A equals 1 asymptotically, but never reach or exceed it. The rotation of black holes affects their environment profoundly. Jets from rotating supermassive black holes reshape galaxy clusters. The jets heat intergalactic gas, prevent cooling, suppress star formation across millions of light years. This feedback regulates galaxy growth. Without it, galaxies would consume all their gas-forming stars much faster. They would burn out, become dead ellipticals within billions of years. But jets from central black holes prevent this. They keep gas hot, reduce star formation rates, extend galaxy lifetimes. The rotation of supermassive black holes influences the evolution of structure in the universe, not just locally, but on the largest observable scales. Here is what disturbs about rotation at these extremes. Neutron stars spinning hundreds of times per second, barely holding together against centrifugal forces. Black holes rotating so fast they drag spacetime around them, creating regions where nothing can stand still. Galaxy clusters rotating over billions of years, organizing the distribution of matter across the cosmos. All of this emerges from angular momentum conservation, the same principle that explains why figure skaters spin faster when pulling in their arms. But applied to objects with gravitational fields so strong they warp space and time, applied to conditions so extreme that matter exists as nuclear pasta and quark-gluon plasma, applied to scales so vast that light takes millions of years to cross them. Rotation is not optional, not accidental, but fundamental. Angular momentum has been woven into the universe since quantum fluctuations in the first instance after the Big Bang. Every rotation we observe today traces back to those primordial perturbations, amplified by gravitational collapse, redistributed through collisions and mergers and tidal interactions, but never destroyed, never created from nothing, only moved from one object to another, from one form to another. The rotation of a millisecond pulsar and the rotation of a galaxy supercluster both preserve information about the early universe. Both are fossils of cosmic history, encoded in angular momentum, and both will persist until the universe itself ends, until all stars die and all black holes evaporate and nothing remains but radiation cooling toward absolute zero in an infinitely expanding void. But even then, angular momentum will be conserved, distributed across photons and gravitons, and whatever particles remain, each carrying infinitesimal angular momentum, collectively preserving the total that existed at the beginning. This is what makes angular momentum truly fundamental, more permanent than stars, more enduring than galaxies, more persistent than space and time themselves. It is the universe's memory, the record of everything that has ever spun, and it will remain until the last moment of cosmic time. a testament to the fact that the universe began not from stillness but from motion. That rotation was built in from the start, that nothing has ever been or will ever be truly at rest. This brings us to the final question. If everything within the universe rotates, does the universe itself rotate? Does the cosmos have net angular momentum? Is there some preferred axis around which all matter spirals? This question ventures beyond established physics into cosmology's deepest mysteries, and the answer will determine whether rotation is truly universal, whether angular momentum extends to the largest possible scale, whether the universe remembers not just the spins of its components but possesses its own cosmic rotation dating to the moment of creation. This is where we turn next, to the rotation of the universe itself, to the possibility that everything we have discussed is merely local motion within a cosmos that rotates as a whole, to the final frontier of angular momentum, the ultimate test of whether rotation is truly fundamental, or whether the universe alone among all things remains still. There is a question that will make you reconsider your place in the cosmos. We have established that planets rotate, that stars spin, that galaxies spiral through space, that neutron stars complete hundreds of rotations per second, that black holes drag spacetime around them, that everything observable possesses angular momentum. But this raises a deeper question. If every component of the universe rotates, does the universe itself rotate? Is there some cosmic spin axis around which all of existence spirals? Does the universe as a whole possess angular momentum? Or is cosmic rotation somehow cancelled, balanced, summed to zero across all scales? The answer determines whether angular momentum is truly fundamental or whether it is merely a local phenomenon within a non-rotating cosmos. Picture what a rotating universe would mean, not individual galaxies rotating within space, but space itself rotating, the entire fabric of space-time spiraling around some cosmic axis. In such a universe, there would be a preferred direction, an axis of rotation pointing to specific coordinates in the sky. Matter and energy would orbit around this axis, not because local forces push them, but because the geometry of space-time itself possesses net angular momentum. Light would spiral as it propagates. Time would flow differently for observers moving in different directions relative to the rotation axis. Causality itself might be violated. Closed time-like curves could exist, paths through space-time that loop back to their starting point, allowing time travel into the past. This is not science fiction. It is a legitimate solution to Einstein's field equations. In 1949, the mathematician Kurt Gödel discovered that general relativity allows rotating universes. Gödel was working at the Institute for Advanced Study alongside Einstein. He was exploring cosmological solutions to the field equations. Most cosmological models at the time assumed the universe was isotropic and homogeneous, the same in all directions, the same at all locations. This assumption simplifies the mathematics dramatically. It leads to the Friedmann-Lemaitre, Robertson-Walker metrics, describing expanding universes, the standard Big Bang cosmology. But Gödel asked what happens if we drop the isotropy assumption. What if the universe rotates? He found exact solutions to Einstein's equations describing rotating universes. These Gödel solutions have remarkable properties. They do not expand. They exist in a steady state, with rotation providing the repulsive effect that prevents collapse. More disturbing, they contain closed time-like curves, paths through space-time that return to the same space and time coordinates from which they departed. Travel along such a curve, and you arrive back at your starting point before you left. Time travel becomes possible, not through exotic wormholes or faster-than-light travel, but through the natural geometry of a rotating universe. Einstein was troubled by this result. He had always been uncomfortable with time travel implications in general relativity. Rotating universes with closed time-like curves seem to violate causality. What happens if you travel back in time? and prevent your own departure, the grandfather paradox. These logical contradictions suggested something was wrong either with the mathematics or with nature. Either Gödel's solutions were unphysical, or our understanding of time and causality required revision. The resolution came from observations. Gödel universes make specific predictions. If the universe rotates, there should be a preferred direction in the sky. The cosmic microwave background radiation should show systematic patterns. Temperature and polarization should depend on direction in ways that reveal the rotation axis. Galaxies should preferentially rotate in one direction rather than being randomly oriented. Large-scale structure should show spiral patterns aligned with cosmic rotation. These signatures would be difficult to miss if rotation were significant. Astronomers have searched for these signatures for decades. The most sensitive measurements come from the cosmic microwave background. The CMB is light emitted roughly 380,000 years after the Big Bang. It has traveled through space for 13.8 billion years, carrying information about the early universe. If the universe rotates, the CMB should preserve evidence of that rotation. Temperature fluctuations should be correlated with rotation axis. Polarization patterns should show systematic deviations from random. The CMB is an exquisitely sensitive probe of early universe geometry. The COBE satellite measured the CMB in the 1990s. WMAP refined these measurements in the 2000s. Planck provided the highest resolution maps in the 2010s. These missions measured temperature fluctuations at the level of microkelvin, parts per 100,000 variations from the mean temperature of 2.7 Kelvin. They measured polarization patterns with precision exceeding 1%, and they found no evidence for cosmic rotation. The CMB is isotropic to within measurement uncertainty. Temperature fluctuations show no preferred direction. Polarization patterns are consistent with quantum fluctuations in the early universe, with no systematic rotation component. This does not completely rule out cosmic rotation. The universe could rotate slowly enough that current measurements cannot detect it, but it places strong limits. Any cosmic rotation must be extraordinarily slow. The rotation period must exceed billions of years, probably exceeding the current age of the universe. This means the rotation has negligible effect on observable physics. The universe behaves as if non-rotating for all practical purposes, even if technically it possesses infinitesimal angular momentum. Some researchers have claimed marginal detections of cosmic rotation. Statistical analyses of galaxy orientations suggesting slight preferences for certain rotation directions. But these claims have not been confirmed independently. Most cosmologists believe the universe is non-rotating to within observational limits. The standard cosmological model assumes zero net angular momentum, and this assumption is consistent with all available data. But why should the universe be non-rotating? If angular momentum is so fundamental, if everything within the universe spins, why does the universe itself not rotate? The answer involves how the universe began. The Big Bang was not an explosion into pre-existing space. It was an expansion of space itself. Initially, the universe was infinitesimally small. Quantum fluctuations determined its properties. Among these properties was angular momentum. The net angular momentum of the observable universe was set by quantum uncertainty in the first moments. Quantum mechanics allows zero angular momentum. In fact, for certain symmetric states, zero angular momentum is the most natural outcome. The wave function describing the early universe could have had zero net angular momentum, while still containing local fluctuations that created rotation at smaller scales. These local fluctuations grew through gravitational instability. They became the rotating structures we observe today: galaxies, stars, planets, all rotating. But their angular momenta are randomly oriented. Some galaxies rotate clockwise, others counterclockwise. The orientations are random. When you sum the angular momenta of all galaxies, the result approaches zero. The universe as a whole is non-rotating, even though its components rotate vigorously. This is like a cloud of gas, where individual molecules move rapidly, but the cloud as a whole is at rest. The molecular velocities are random. Averaged over many molecules, the net momentum is zero. Similarly, galactic rotations are random. Averaged over many galaxies, the net angular momentum is zero. The universe contains enormous rotational energy, but it is distributed in ways that cancel when summed globally. The cosmos has no preferred rotation axis because rotation is local rather than global. There is a deeper reason to expect zero cosmic rotation. Angular momentum conservation implies that the total angular momentum of a closed system remains constant. If the universe is closed, its total angular momentum cannot change. It was determined at the Big Bang and has remained constant since. But what was it at the Big Bang? If the initial state had perfect symmetry, the total could be exactly zero, not merely small, but mathematically zero. Every rotation in one direction balanced by equal rotation in the opposite direction. This would explain why we observe zero net angular momentum, despite observing rotation everywhere locally. Some cosmologists propose that the universe underwent inflation immediately after the Big Bang, a period of exponential expansion, lasting perhaps 10^-32 seconds, during which the universe grew by factors exceeding 10^26. Inflation smooths out initial conditions. Any pre-existing rotation would be diluted by the enormous expansion. The observable universe today corresponds to a tiny patch of the pre-inflation universe. That patch might have had negligible angular momentum simply by chance. After inflation, this small region expanded to become the entire observable universe, inheriting the zero angular momentum of the original patch. Regions beyond our cosmic horizon might rotate, but we cannot observe them. Within our observable universe, angular momentum sums to zero, but measurements can never prove exact zero, only that rotation is smaller than measurement precision. Perhaps the universe rotates extremely slowly, one rotation every trillion years. This would be undetectable with current technology, but would technically mean the universe possesses angular momentum. If so, we need to ask where that angular momentum came from. What process at the Big Bang created net rotation? And why is it so small compared to local rotations we observe? One possibility involves quantum fluctuations. In quantum field theory, the vacuum is not truly empty. Virtual particles constantly appear and disappear. These quantum fluctuations have angular momentum. Most of the time, they cancel, a virtual particle-antiparticle pair with opposite angular momenta. But occasionally, fluctuations do not cancel perfectly. Small imbalances occur. Over cosmological timescales, these imbalances might accumulate into measurable cosmic rotation. This effect would be extraordinarily small, but it would be non-zero. The universe would rotate, but with periods exceeding the age of the universe by many orders of magnitude. Another possibility involves topology. If the universe is not simply connected, if it has non-trivial topology like a torus or more complex manifold, then global rotation could exist even with locally isotropic expansion. Imagine space wrapping around to form a closed loop in one direction. Travel far enough in that direction, and you return to your starting point. Such a universe could have net angular momentum associated with the topological structure. Photons traveling around the universe would experience frame-dragging effects, but these effects might be too subtle to detect unless the universe is much smaller than current estimates suggest. Most evidence suggests the universe is flat or nearly flat with simple topology, but we cannot rule out complex topology beyond our cosmic horizon. Now consider what happens if future observations did detect cosmic rotation. If someone found undeniable evidence for a preferred rotation axis in the CMB or in galaxy orientations, this would revolutionize cosmology. It would require abandoning the cosmological principle, the assumption that the universe is isotropic and homogeneous. We would need new models incorporating rotation from the beginning. The standard FLRW metrics would be insufficient. We would turn to Gödel solutions or similar rotating cosmologies. And we would need to address the time travel implications. Gödel universes allow closed time-like curves, paths through space-time that loop back on themselves temporally. An observer following such a path would experience normal causality locally. Time would flow forward as always. But the path through space-time would curve in such a way that the observer eventually returns to the same space-time coordinates from which they started. This creates paradoxes. What if you meet yourself? What if you prevent yourself from beginning the journey? These questions have troubled physicists and philosophers for decades. Several resolutions have been proposed. The Novikov self-consistency principle suggests that only self-consistent histories are possible. If you travel back in time, you cannot change the past because the past already includes your time-traveling intervention. Any attempt to create a paradox would fail through some mechanism. Quantum mechanics might provide another resolution. Many worlds' interpretation suggests that changing the past creates a branch. You travel back, but to a different timeline. The grandfather paradox is avoided because killing your grandfather affects a different version of history, not the one from which you originated. But these resolutions feel unsatisfying. They avoid logical contradictions by invoking mechanisms that cannot be tested. Most physicists hope that time travel remains impossible, that some principle we do not yet understand prevents closed time-like curves in realistic spacetimes. Stephen Hawking proposed the chronology protection conjecture, the idea that laws of physics conspire to prevent time travel even when the equations allow it. Perhaps quantum effects cause closed time-like curves to be unstable. Virtual particle loops build up infinite energy densities that prevent curve formation. This is speculative, but it provides hope that causality is preserved even in rotating universes. Fortunately, observations suggest our universe is not rotating significantly. We do not need to worry about time travel paradoxes arising from cosmic geometry. The universe behaves as if non-rotating, and this is consistent with angular momentum conservation if the total angular momentum was zero at the Big Bang. Local rotations emerged from quantum fluctuations. Gravitational collapse amplified these fluctuations. Structure formed, galaxies spun up, stars formed, planets coalesced. Everything acquired rotation through local processes, but the sum remains zero. The universe remembers no net rotation from its origin. Yet we should not take this for granted. Science progresses through testing assumptions. The assumption of non-rotation is well supported, but not proven absolutely. Future observations with more sensitive instruments might detect subtle rotation signatures, perhaps through CMB, polarization measurements exceeding Planck satellite precision, perhaps through statistics of galaxy orientations in surveys covering billions of galaxies, perhaps through gravitational wave astronomy detecting systematic frame-dragging effects. We should remain open to the possibility that the universe rotates, even if current evidence suggests otherwise. Consider what we have learned across these three explorations. Rotation is universal, from planets to pulsars, from asteroids to black holes, from molecular clouds to galaxy clusters. Everything spins. This rotation derives from angular momentum conservation, a fundamental law emerging from rotational symmetry in nature. Angular momentum cannot be created or destroyed, only transferred between objects. The universe remembers every rotation that has ever occurred. Every spin since the Big Bang contributes to the current angular momentum distribution. Nothing is exempt. Nothing stands still. The speeds are staggering. Earth rotates at 1,600 kilometers per hour. Jupiter completes rotations in 10 hours despite enormous size. Millisecond pulsars spin hundreds of times per second. Black holes rotate so fast they drag spacetime around them. These rotations are not independent. They are connected through gravitational interactions and tidal forces and collisions that exchange angular momentum. The solar system's rotation connects to the Milky Way's rotation. The Milky Way's rotation connects to the local group's tumbling motion. Everything participates in a hierarchy of nested rotations, extending from quantum scales to cosmological scales. But the cosmos itself appears non-rotating. The universe has no preferred spin axis, no net angular momentum. This is remarkable. It suggests that despite rotation being fundamental to all structures within the universe as a whole emerged from a symmetric state. The Big Bang created quantum fluctuations with random orientations. These fluctuations grew into rotating galaxies and stars and planets, but their rotations cancelled when summed. The result is a universe that appears isotropic, the same in all directions, with no evidence for cosmic rotation. Here is what should disturb you about this conclusion. Angular momentum is conserved. This is law, yet the total angular momentum appears to be zero, not small, zero. Every rotation we observe is balanced by an equal and opposite rotation somewhere else. The universe is like a perfectly balanced gyroscope spinning furiously internally, but with no net angular momentum. How is this possible? How can something so fundamental be exactly zero, rather than some small but non-zero value? The answer must lie in the initial conditions, in the symmetry of the Big Bang, in the quantum state that gave rise to classical spacetime. Perhaps the wave function describing the early universe had zero angular momentum eigenvalue, perfect spherical symmetry, no preferred rotation axis. As the universe evolved, this symmetry was broken locally. Fluctuations grew, structures formed, rotation appeared, but the total remained zero because angular momentum cannot be created from nothing. Local rotations emerged in pairs. For every galaxy rotating clockwise, another rotates counterclockwise. For every planet spinning one way, another spins oppositely. The pairings are not obvious because space is vast and rotations are distributed across cosmic distances. But if you could sum all angular momenta across the observable universe, the result would be zero. This is one of the deepest facts about reality. The universe began from symmetry, perfect balance, zero net everything, angular momentum, linear momentum, electric charge, all summing to zero. As the universe expanded and cooled, symmetries broke, structures formed, imbalances appeared locally, but globally, the totals remained zero. This is why charge is conserved, why matter and antimatter are nearly equal, why cosmic rotation is undetectable. The universe remembers its symmetric origin, even as local asymmetries dominate our experience. Yet within this symmetric universe, rotation is ubiquitous, essential, unavoidable. Every structure that forms through gravitational collapse acquires rotation. Conservation of angular momentum guarantees it. A cloud with even infinitesimal rotation spins up as it contracts. A collapsing protostar becomes a rapidly rotating star. A neutron star core becomes a millisecond pulsar. A black hole forms spinning near the extremal limit. Rotation is the destiny of all collapsed objects. It cannot be avoided. It emerges inevitably from the mathematics of angular momentum conservation. This means rotation is not accidental but necessary, not a coincidence but a consequence of fundamental physical law. If the universe contained no angular momentum at all, if every quantum fluctuation were perfectly symmetric, then perhaps nothing would rotate. But quantum mechanics forbids perfect symmetry. Uncertainty principle demands fluctuations. These fluctuations include rotation, and once rotation exists at quantum scales, it propagates to larger scales through gravitational amplification. The rotation we see today in galaxies and stars and planets traces back to quantum jitters in the first instance after the Big Bang. Rotation is quantum mechanical in origin, classical in expression, universal in application. There is something profound about this connection between the very small and the very large. Quantum fluctuations, smaller than atomic nuclei, determining the rotation of objects larger than solar systems. The same fluctuations that created density variations leading to galaxy formation also created the angular momentum that makes those galaxies spiral. The same uncertainty that prevents electrons from having definite positions also prevents the early universe from having zero rotation everywhere. Quantum mechanics at Planck scales influences structures at cosmic scales. This is not mysticism. It is physics, rigorous mathematics, tested predictions, confirmed observations. We are part of this story. Earth rotates because the solar nebula rotated. The solar nebula rotated because the molecular cloud that formed it rotated. The molecular cloud rotated because the galaxy rotates. The galaxy rotates because quantum fluctuations in the early universe gave it angular momentum. Your existence depends on rotation. Without Earth's rotation, the planet would be tidally locked to the sun. One hemisphere eternally scorching, the other frozen. The temperature extremes would make life impossible. Earth's rotation creates the day-night cycle, moderates temperatures, drives atmospheric circulation and ocean currents, generates the magnetic field through dynamo action in the liquid outer core. This magnetic field shields the surface from solar wind. Without it, Earth's atmosphere would be stripped away like Mars's atmosphere was billions of years ago. You exist on a rotating planet because rotation is fundamental to the universe. Your body contains iron forged in stellar cores, stars that formed from rotating molecular clouds, stars that exploded as supernovae, creating the heavy elements necessary for life. The rotation of those stellar cores determined whether they formed neutron stars or black holes after explosion. The rotation influenced the geometry of the supernova blast, the distribution of ejected material, the enrichment of the interstellar medium with the elements that eventually became you. Rotation is written into your atomic structure, into the iron in your blood, into the calcium in your bones. You are made of rotation, assembled from materials processed through billions of years of cosmic spinning. And when you die, your atoms will continue participating in rotation. They will return to Earth, be incorporated into other organisms or rocks or oceans. Eventually, Earth itself will be destroyed when the sun becomes a red giant. The atoms will be vaporized, dispersed, perhaps incorporated into new molecular clouds, new stars, new planets, and those new structures will rotate because angular momentum is conserved, because the rotation that exists today will persist for billions of years. The universe will continue spinning, stars will form and die, galaxies will merge and disperse, black holes will evaporate through Hawking radiation over timescales of 10, 100 years, and still, angular momentum will be conserved. Even the radiation emitted by evaporating black holes carries angular momentum. The photons and gravitons possess spin. The conservation law holds until the final moment of cosmic time. This is what makes rotation truly fundamental. More permanent than matter, more enduring than energy, as fundamental as space-time itself. Angular momentum is woven into the structure of reality at the deepest level. It emerges from rotational symmetry, the fact that physics works the same regardless of orientation. This symmetry is built into the fabric of existence. It cannot be violated, cannot be circumvented. It is law in the most absolute sense, and its consequence is that rotation persists forever. The universe began with zero net angular momentum. It will end with zero net angular momentum. But between beginning and end, everything spins. We have asked why everything rotates. The answer is angular momentum conservation. We have explored the fastest rotations in nature, millisecond pulsars and rotating black holes. We have questioned whether the universe itself rotates. The answer appears to be no. But within that non-rotating cosmos, rotation is universal, unavoidable, essential. From the quantum fluctuations that seeded galaxy formation, to the tidal interactions that lock moons to planets, from the accretion disks that spin up neutron stars, to the frame-dragging effects near black holes, rotation is everywhere. It is the signature of motion, the mark of time's arrow, the record of cosmic history, encoded in angular momentum. And here is the final disturbing truth. Rotation is directional. It breaks symmetry. When something rotates, it defines an axis, a direction that is different from other directions. This seems to violate the isotropy of space. How can space be the same in all directions if rotation singles out preferred axes? The resolution is that rotation is relative. The axis is defined by the rotating object, not by space itself. Space remains isotropic, but objects within space break that symmetry through rotation. Each object has its own axis, its own angular momentum vector. These vectors point in random directions. When averaged, they cancel. But individually, each rotation defines a local preferred direction. This is how isotropy and rotation coexist. Global symmetry with local asymmetry. You live in a rotating universe. Not a universe that rotates as a whole, but a universe where everything within it rotates, where angular momentum governs motion on all scales, where the conservation law shapes the evolution of structure across cosmic history, where rotation emerged from quantum uncertainty and will persist until the heat death of the cosmos. This is reality, not abstract theory but observed fact. Every telescope observation confirms it, every spacecraft mission demonstrates it, every calculation predicts it, every experiment validates it. The universe is a place of motion, of spin, of angular momentum conserved across billions of years and trillions of light years. Nothing is still. Nothing can be still. Because to be truly at rest, an object would need zero angular momentum, and quantum mechanics forbids zero exactly. Uncertainty prevents it. There is always some residual rotation, some infinitesimal spin, some tiny angular momentum that connects every object to the cosmic rotation network that began with the Big Bang and will end only when the universe itself ends. This is what we discover when we ask why everything spins. Not a simple answer, but a profound truth about the structure of reality. Rotation is not optional, not incidental, but necessary, fundamental, universal. It is the way the universe moves, the pattern it follows as it evolves from quantum symmetry to classical complexity, the mechanism by which structure forms and persists. The reason galaxies have spiral arms, and planets have day-night cycles, and pulsars emit regular pulses, and black holes power quasars. Everything spins because the universe is not static. It never has been. It never will be. Motion is fundamental. Angular momentum is conserved. And rotation is the clearest expression of both principles. From the smallest scales to the largest, from atoms to galaxy superclusters, from the beginning of time to its end, everything rotates, everything spins. Everything participates in the cosmic dance of angular momentum that defines what it means for the universe to exist in time. This is not poetry, not metaphor, but physics, pure, rigorous, beautiful, and fundamentally true about the reality in which we find ourselves embedded, spinning through space. always spinning, never still, forever in motion until the final darkness comes, and even then, the rotation will persist, encoded in the last photons carrying the last traces of angular momentum into the infinite future of an empty, expanding cosmos.